In today's lecture, we're going to cover principal component analysis, or PCA. PCA is an unsupervised method for dimensionality reduction. If we have a large number of features, it can make it really challenging to train a classifier. Most of the time, if we have a lot of features, it means a lot of them are either redundant or irrelevant, or they rely too much on each other, and we want to reduce the number of features so we can learn a better classifier that generalizes better. We'll use PCA to reduce the number of features. So PCA is referred to as a dimensionality reduction technique because the number of features is equal to the dimensions, and so we're going to reduce the number of dimensions. We're going to go through a quick review of eigenvalues and eigenvectors because PCA builds on this, and so we'll need to have an understanding of it. You may remember from linear algebra that we can have a formula like so. AV equals lambda V, where A is a matrix and lambda is an eigenvalue, and then V is going to be an eigenvector. So eigenvectors and eigenvalues don't exist just in the ether. They are related to a particular transformation, A. So a matrix has eigenvectors and eigenvalues associated with it. Eigenvectors and eigenvalues don't exist on their own. An eigenvector V is one that doesn't change direction when the transformation A is applied. It simply changes length. We can see that in the equation. So that's what the equation on the top says in English. It says I can apply a transformation A to this vector V, and I will get V back out, but scaled by some value lambda. Okay, so it doesn't change direction, it simply changes length. Each eigenvector has a corresponding eigenvalue. So for every V for a matrix A, there is a lambda. We can calculate eigenvectors and eigenvalues using what's called the characteristic equation. We take A and subtract lambda I. Remember, I is the identity matrix. We take the determinant of the resulting matrix and we set it equal to 0. Let's run through an example. If we have this matrix A equals 0, 1, negative 2, negative 3, then we calculate the determinant of A minus lambda I, which is going to look like this. The determinant is then going to be lambda squared plus 3 lambda plus 2, which equals 0. We can then factor this or use the quadratic formula to get the values for lambda 1 and lambda 2. Here we get negative 1 and negative 2. We can then use our lambda values to calculate our eigenvectors. Remember that each eigenvector has a lambda, so we can use lambda 1 to figure out what eigenvector 1 should be. We do that by using the equation for an eigenvalue eigenvector. AV equals lambda V. We move the right side to the left side, and then we have 0 on the right side. And then all we do is solve for lambda 1. So we have this equation at the bottom, and we have two equations because of it. So if you multiply the V by this matrix 1, 1, negative 2, negative 2, you'll get V11 plus V12 equals 0. So you'll get V11 equals negative V12. Or you can do the bottom line, which is negative 2V11 minus 2V12 equals 0. You'll get the same result either way, so you really only have to use one of the equations. Basically what this says is that V1 has the opposite sign of V2. So V1, the vector V1, is any scalar multiple of positive 1, negative 1. We can similarly solve for V2 using the bottom line. Here we'll get negative 2 V21 plus negative 1 V22 equals 0, which just gives us 2 v21 equals negative v22. And so this is also some scalar multiple of 1, negative 2. So all you really do here is you just plug a number in for v21, and that'll give you the value for v22. And then you know it's any multiple of that. Generally, you're going to want your eigenvectors to be unit vectors. Remember, unit vector means length 1, so all you do is divide by the length of the vector, and you'll get these values. So you'll get 1 over root 2, negative 1 over root 2, negative 1 over root 5, and 2 over root 5, okay, corresponding to those eigenvalues up above, negative 1 and negative 2. Now back to PCA. Now that we have this foundation with eigenvalues and eigenvectors, we can just walk through the steps of PCA. The idea is we have some original set of data with some number of features, and we want to produce a new transformed set of data that has fewer features. So here are the steps. We're going to calculate the average for each feature. We're going to subtract the mean of each feature from every sample. We're going to divide each feature by its standard deviation, and then we're going to use all of this centered and standardized data to create a matrix Z. We're going to compute the covariance matrix. We're going to compute eigenvectors and eigenvalues of the covariance matrix. We're going to sort the eigenvalues and the corresponding eigenvectors, largest to smallest. We're going to select k eigenvectors. K is usually less than d, where d is the original dimension of the data. We're going to call this U, and we're going to project Z onto U to get our transform data. Let's start with this data set, okay? So the data is listed on the left, so if you wanted to create a program to practice PCA, you can do that because I've provided the data here for you. But we're going to kind of mostly look at the graph to get a sense of what PCA is doing. Let's calculate the average for each feature. So we do that just in the standard way. There's 13 samples. We add all of the x1s together, divide by 13, add all the x2s, which I'm switching between x2 and y here for some reason, but ignore the notation issue. And you're going to divide by 13 again. So you'll get the average for x1 is 3.07, and the average for x2 is 3.23. We're going to subtract that average that we just calculated from every sample. So we have our original data. We're going to subtract the average for x1 from all of the x1s, and we're going to subtract the average of x2 from all the x2s, and then we get this new data on the right-hand side. So now the data is centered. So it's actually centered around 0. So we have the data looking like this now. So we've basically just shifted it to the left and down so that all the data has a mean of 0. All of the features have a mean of 0. Now we're going to divide each feature by its standard deviation. If I require that you do the full PCA algorithm on a test or whatever, you usually won't have to do the standard deviation because the numbers get really messy. But we're going to use it right now to go through the whole method. So the standard deviation equation is just this. So for each feature, we're going to have a standard deviation. So for a feature I, we sum over all samples, and we subtract the mean, which is now 0. And then we square that, and then we take the square root after we sum those all up. So for feature 1, the standard deviation is 1.44, and for feature 2, it's 1.96. So again, we divide each sample by this. So we transform from the centered data all the way to the centered and standardized data on the right-hand side. This is now our data matrix Z. Okay, so this is our standardized centered data. We're going to call it Z. We're going to compute the covariance matrix, ZTZ. And the covariance matrix gives us some sense of how each feature changes with respect to others. So all we do is multiply Z transpose by Z. This is going to give us a 2 by 2 matrix. It's always going to be D by D, where D is the dimensionality of the original data. Now we're dealing with something much simpler, as opposed to this mess back here. The next step is to compute the eigenvectors and eigenvalues of the covariance matrix. Good thing we're experts at that now. So we have ZTZV equals lambda V. So we use the characteristic equation and we get the determinant of this, and we set it equal to 0, which is going to look like this. The final equation we get is lambda squared minus 13.19 lambda minus 1.19. I don't expect you to be able to factor this, so you will be using the quadratic formula, which is so exciting. If you can't remember it, there's a little thing to help you. A negative boy couldn't decide whether or not to go to a radical party and be square and miss out on 4 awesome chicks, and it was all over at 2 a.m. It's terrible, I know, but somebody told it to me when I was in 8th grade, and I haven't forgotten it, so hopefully it'll help you remember as well. We use this equation and we calculate lambda 1 and lambda 2. Now we have lambda 1 and lambda 2, we need to figure out what the eigenvectors are. Okay, so we just start with lambda 1, and we use the top line here, and we find that v1 equals 7.3828 v2. So we create this vector where v1 is 7.38 and v2 is 1. Now we do the same thing with lambda 2, and we get that v2 is going to be negative 0.84 and 1. So we're going to sort the eigenvalues and eigenvectors largest to smallest. So the largest eigenvalue is obviously lambda 1, and we're going to take that vector. So we need to standardize these, we need to normalize these, remember? So we're going to make them length 1, and in doing so, v1 becomes 0.99, 0.13, and v2 becomes negative 0.64, 0.76. Now we're going to select k eigenvectors. We're going to call this u. We only have 2 dimensions to start with, so we're just going to choose k equals 1. And then we're going to project the data onto this 1 dimension. We're going to do that by taking the centered and standardized data and just multiplying it by this vector. So now we've changed the dimensionality of the data from 2 to 1. So we took the data at the top here in the dark plot, and we actually projected it down to the data that's down below. So now it's on 1 dimension, and we can see how the points map to each other. On the left-hand side, we have those 2 points where it's some function of the x1 and x2. And we have the 3 points after that, 3 points, 2 points, 3 points. And they're all some function of x1 and x2. We can project the data back onto the original space, and we get this. So this looks just like the data we had, except for we're getting rid of that 2nd dimension information. So what's really cool about principal component analysis is that it explains the variance in the data. So the first principal component, which is going to be the eigenvector with the largest eigenvalue, explains most of the variance in the data. That means this. We can see that the data varies significantly over the first principal component. So this is me just plotting the first principal component. And we see that the data varies significantly over that component, whereas with the second component, it doesn't vary as much. So the idea is to get rid of those less varying components and describe the data in fewer dimensions. In this lecture, we covered what is PCA, the steps of PCA, and how it's used to project data into a lower dimension.